Hey everyone, today I'll explain my thought process and how I solved this LeetCode Hard 2306 naming a company problem. And the problem appeared in a recent LeetCode weekly contest, and as you can see, the success rate is quite low, and only 600 people have managed to solve this problem in the contest. And we'll see how to approach these kinds of problems and how to solve them. Right, let's start. So in the problem we are given an array of strings called ideas, and each the 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 array of string represents a list of names to be used in the process of naming a company. And the process of naming a company is as follows, right? We have a few conditions. We have a few steps to name a company, and first step is to choose two distinct names from ideas and call them idea A and idea B. Right? We choose two strings from this array and call them idea A and idea B, and then we swap the first letters of both the strings with each other. Then we get a new string, right? Two new strings, and then if both of the new names are not found in the original ideas in the original list, then the name idea A concatenated with idea B with a space is a valid company name. Otherwise, it's not a valid name. Okay. So we are doing three things here. We are choosing two distinct names, and then we are swapping the first letter, and then we are deciding, and then we are concatenating and then deciding, right? And then deciding, before concatenating, we need to check if the modified new strings we got after swapping are not present in the string in the original array of strings, and then we are deciding whether it's a valid company name or not. Okay. And we need to return the number of distinct valid names for the company. So we need to return number of distinct concatenations of those strings, right, for the company. Okay. So we have few examples, and one more thing to note here is that all strings in ideas, the given array of strings, are unique. So there won't be a situation in which we choose two strings at different indices and they end up being the same string, right? So the first condition, that two distinct names, is just basically uh, reduces to saying that choose two strings from the given string, right? So we can say that first condition is just, instead of saying two distinct, it just means choose two names from ideas and call them idea A and idea B. So the term distinct here is redundant because, as I said, the list is unique. So the first condition is we have seen. Next, yeah, they have given few examples, and we can see here we have four strings, and the total possible concatenations you can see here are six valid concatenations, and they are saying therefore, yeah, there are total six distinct company names, and the following are some invalid selections. Okay, so they're explaining why it's invalid. So here it's invalid to choose coffee and time because the name toffee formed after swapping already exists in the original array. You can see here, if we take these two strings and swap the first letters, we will get toffee and sime, right? CIME, sime, and toffee is present in the string, so it's not a valid pair. So the same applies for their reverse also, like time and toffee. Okay, so yeah, and then the next case is time and toffee. Yeah, here you can see, if we just swap the first two letters, we'll just end up getting the same pair, right, again, and they both exist in the string, so it's not valid too. And then the next pair is this coffee and toffee. If we swap both of the first letters, we'll again end up getting toffee and coffee. Both of those uh, both the strings exist in the original array, so it's not valid, right? So here, after going through these invalid cases, you can just rule out few cases, right? So if the we cannot pair two strings with same starting letters. We can say that after seeing this example, seeing this pair. So this is one possibility, right? And we can also say that if a comma aj is a valid pair, then what is it? Donuts comma coffee. Then donut, if coffee comma donuts is a valid pair, then donuts comma coffee is also a valid pair, right? So if a comma aj is a valid pair, aj comma a is also a valid pair. So everything is everything occurs in a double. So that's the thing. Similarly, if a comma aj is not valid, then aj comma a will also be not valid, right? And we need to return all the possible valid strings. Okay. Right. So let's look at this case. Here we can see if we have only two strings, and if we just swap the first letters, we'll just end up getting the same string since the suffix is same. So yeah, and one more thing you could have noticed here is that when we swap the first two letters, we got both the new strings which are formed are equivalent to the initial strings we had, which are coffee and toffee, right? So this happened because we have a same suffix. Both the strings have same suffix, and the only difference occur in the first letter, right? So this is a important observation to make here. These two observations, they are very important. We'll be using these two observations to solve the problem actually. Similarly, here both the suffixes are same. You can see. Hence, swapping the first two letters doesn't have any effect over the answer. So hence we are returning 0. And constraints, constraints, we can see that the length of the array is around 5 times 10 power 4, and the maximum length of each string could be 10. So 1 to 10, so it won't be empty. And we are also given that each string contains only lowercase English letters, and also that the entire array contains only unique strings. Okay. So after looking at the constraints, we can conclude that order of n square won't be possible because 5 times 10 power 4 square would cross 10 power 8 already, so we can't do that. So anything better than order of n squared is required here, I think. Yeah, anything better than order of n squared should be better. So let's see how to do that, right? So let's just see how will we do the brute force like order of n squared, right? How will we do that? So the way we do order of n squared is we iterate over the array, and every time we meet a string, we just either we go on to the right of the current index and check with what all strings we can pair this current string, right? So we can do that, or else we can do for every current string we can go to the left and check for what all strings we can pair the current index with, and then we can add the answer, right? So to check if we can pair both the strings, like to check if we can have a we can pair donuts with coffee, we need to check if both the strings satisfy these 4 conditions, right? So the first condition is already satisfied, as I said, the list contains only unique elements, and the second condition so second is not actually a condition, it's just an operation. And the second condition is that after swapping, both the strings should not be in the original array, right? So let's say we are doing brute force, right? We have a for loop from I equals 0 to n minus 1, and we have another for loop for j equals 0 to I minus 1, right? And we need to check and check if ai and aj are a valid pair. If it's a valid pair, we'll increment the answer and we'll return the answer. So this is how the brute force solution will be, right? And to do this check, so these two things itself will cost us order of n square. And to do this check, let's see how to do the check, right? So we need to check after swapping the first letter, the strings newly found should not be in the original array, right? So how to do that? So either we can iterate over the array again and check in the check. Let's say we have another function, check function a comma aj, and we need to check after doing some operations whether this newly formed string is present in the array or not. So either we can have one for loop and iterate over all the values in array a and check if a is not equal to ak and aj is not equal to ak, and then we can do like that. So this will cause another order of n times, so our solution will become order of n cube, right? So we don't need to do that. Instead, a basic, we can use a basic data structure and we can reduce this time complexity, right? So if we use a instead of going to an entire array, if we just store all the strings in an ordered set, right? In an ordered set, we can check if a or aj is present in the original array or not in order of log n time, right? We can do that. So using ordered set. Can we can even reduce this into constant time. Basically, this is not just order of log n because we are not just comparing numbers, right? So it would be, we are comparing strings, so order of log n times the maximum possible length of the string, and maximum possible length of the string here could be 10. So yeah, if we use ordered set, we can have the check in order of log n times n l. And if we use a hash set like unordered set or something, we can do that check in constant time, which is order of l, the length of the string itself, right? So unordered set, right? So either we can do this, but like since this is LeetCode, this will pass. But if this were a code force contest or something, this is not a reliable approach. Unordered set, unordered map, or unordered set, right? So in that case, we can use another data structure. We can use a try to do this check, right? We can store all the strings in a try, and then we can search if the string exists in the try or not in the order of length of the string, right? We can do that. Instead of unordered set, we can use a try and do this. Time complexity would be the same, even the space complexity would be the same. So this is in try, this is guaranteed, but in unordered set, if we don't have a like if you use an unordered map or something and you don't have a proper hash function, so there could be a worst case complexity of linear time. So yeah, this is an approach. So using these approaches, we can reduce this into order of n square times l, so where l is 10 here. So this is how the brute force is done, right? Okay, but we don't need the brute force solution. We need to solve this in an optimal time. Like how can we solve this in even more optimal time, right? So as I said, the expected complexity is either order of n or order of n log n, right? So how can we achieve this time complexity from this time complexity? How do we do that? So we can clearly see that we can't have two nested loops in both of these complexities, right? So we can't have this whole block of whole nested for loop. So let's just remove the for loop. Let me just remove everything. Yeah, so for I in 0 to n minus 1, we cannot have a nested for loop, but we need to determine the answer somehow, right? How do we do? So this is where the important part of this problem comes here. Like for many such problems where we need to find a pair of something, or when we need to map a pair or two values, usually the obvious way to do that would be in order of n squared, and most of the problems would require us to do in order of n or order of n log n, right? So how do we do in general? How do we reduce this order of n squared into order of n in such problems? In those problems which talks about pairs or triples or anything for that matter, right? How do we do that? So initially, how do we do that? Right? Order of n squared. Okay. So in the brute force, what we did was for each value AI, for each value AI current value, we either looked at the right of the current index I, and then try to map each string on the right with the current string AI, or we looked at the left and try to map the current string with the any string present in the left, right? We did either of, like, any, we can do any one of them. So if we just directly do that, it will again become order of n squared, right? Now we have to do the same thing, but we cannot directly do that. We cannot directly go through the entire left part of the current, like if we are at index I, we cannot directly go through all the indices on present at the left of I, right? So we need to do something better. We cannot directly go through either the left or right. Okay. So usually, the technique in which we do this, by the way in which we reduce the order of n squared to order of n or order of n log n and find a optimal solution, it's called as such it doesn't have a name, but people usually call this as fixing an element and finding the answer for that element, and then adding the contribution of that element to the answer, right? So in that case, we'll add the contribution of AI here to answer. So what does this contribution mean? This contribution means with what all possible strings aj such that j is lesser than I, I can map AI. So that would be the count of j, that is count of j. So all valid j in which we can map AI and aj. Okay. So this is an important thing, like fixing an element and then finding the contribution of that element and then adding that contribution to the answer. So that's how we reduce the time complexity from order of n squared to order of n. Okay. So this is the first thing. Now I think how to reduce the time complexity is clear. So now that we have have a high level overview of how to solve this problem, we can move on to actually having a solution. So till now we have seen the brute force solution, and then how to, in general, how to reduce the time complexity of such solutions from order of n squared to order of n or n log n, right? So this is the high level overview of our solution. Okay, so this is how it's going to be. We'll iterate over the entire array, and for each element AI in the array, we'll try to find the contribution of that element to the answer, and then we'll add it to the answer, and then we'll return the answer, right? And for finding the contribution here in this problem, the contribution just means the count of j such that j is lesser than I, and we can map aj with AI. Okay, I hope it's clear. Okay, let's see how to find this contribution. Okay, so in order to find the contribution, we need to check, right? We need to check after swapping the first two letters. We need to check if the newly formed two strings are not present in the array. Okay, let's see how to do that. Okay, let's just again look at the example. I told that these two observations are important, right? So let's again look at those examples. Here we can see that if we have a, let's say we have a for loop. We are iterating from we are iterating from 0 to n minus 1, and ai is just a of I, right? And if we have a, let's say ai is time. Okay, let's say ai is toffee, let's say that. And if we try to go to the left and try to map check if we can map each string to toffee or not, we can see that we cannot map time with toffee, right? Why? Because they have same starting letters, right? So we can conclude that any string aj which has the same starting letter as that of ai is not a valid string, right? This is the first observation we can make. And then the second observation we can make is, if by seeing this example, right, we can see here both the strings have the same suffix. The suffix from one more thing is, so in this throughout the video I will be saying suffix. So suffix in this case means the part where the substring starting at index 1 to the end of the string. Okay, so I am talking about this suffix, not just any suffix. I am talking about the largest suffix of any string. Okay, so in this case we have the same suffix coffee, OFFEE and OFFEE. We have the same suffix, but the only difference between those two strings are the starting letters. So, and it's an invalid case, right? So why it's an invalid case? Because if we just swap the starting letters, we'll just end up getting the same two strings, right, which are already there in the array. So it's invalid. So we can conclude that if we have two strings with same suffix, and note that suffix in the sense the largest suffix, which is basically starting at index 1 and ending at the last index, right? So this thing. So if we have two strings with same suffix, we cannot pair them together. So that's the second observation. So if aj of 1 to n minus 1 is same as ai of 1 to n minus 1, basically the suffix, if the suffix is the same, we cannot map. Okay, let's see if there is any other case in which we can map, in which we can any other invalid case, right? That could be just by looking at the given sample, we cannot decide or conclude upon the total number of invalid cases, right? Let's see if there is any other possibility, right? Okay, let's write down this array again. So we have coffee, donuts, time and toffee. Okay, donuts, time and toffee. Okay, so let's just dry run this example using the brute force and see what are the possibilities, right? So can we map so we have to start from the first index, because only then we can go to the left and check. So can we map donuts with coffee? Yes, we can. So this mapping is possible. Okay, let's come to time. Can we map time with donuts? Yes, we can map. Can we map time with coffee? We cannot. Why? That's this case. That's the first example given. The reason why we cannot map time with coffee is, even though they don't have same starting letters and they don't have the same suffix, one common thing they have is there is another string in the array which have the same suffix of OFFEE, and it starts with the letter T. So when we try to map coffee with time, we swap T with C and we get toffee, and toffee is present in this original array, but we don't want that, right? So how come this happens? So how to check this, right? So this is kind of an indirect way of application. Like here it's very obvious, we can directly check, but here this is not obvious, right? Again we need to check if the swapped thing is present in the string or not. So can we optimize this? Like, is there a possible way to optimize this, of finding whether we can map two strings or not, right? So we saw that we cannot map time and coffee. So how do we optimally check if we can how do we optimally check this indirect way of connection of coffee and toffee, right? Somehow we couldn't map time and coffee, because coffee had a same suffix with toffee, and the toffee ended up having the same letter with the current string. So how come is this possible? Okay, let's say we have one more string in the array with LOFFEE, right? LOFFEE, and we have another string, say lime. Now can we map again lime and coffee? We cannot, because somehow there is another string in the array called loffy, and it has the same suffix as coffee, and the first starting letter of that string is L, which is same as the current string. Okay, so whenever we have a set of strings, with common suffix, we are not able to map our current string to any of those strings, right. So how is this happening? Right. So how is this happening? Like we had coffee, toffee, and loffee, and we couldn't map lime with any of them. We couldn't map lime with coffee because coffee has an. So we have another string similar to coffee which has the same suffix, right? Okay. Let's just see to what all strings we cannot map. Okay. So we couldn't map to coffee. We couldn't map to toffee and loffee. Okay. We had time. We couldn't map it to coffee because there was another string toffee. We had lime. We couldn't map it to coffee because there was another string loffee. Okay. We cannot map lime and loffee because both the starting letters are same. Okay. Can we map lime and toffee? We cannot because there is another string in the array which has same starting letter, which has same suffix and starting letter with L. Okay. Can you see some kind of pattern here? If we couldn't map current string with any of these strings, right? Any of these strings we couldn't map. We couldn't map time with any of these strings. We couldn't map line with any of these strings. So why is that happening? So we can see the reason why is it happening is we can see one common thing with all these strings, right? That common thing is that they have a same suffix. So since they have same suffix, we couldn't map any current string with any of those strings which had the same suffix. So from here we can make a third observation that we can't pair AI with AJ if there is another string with same suffix as AJ and has AI of 0 as starting letter, right? So this is what is happening here, right? The whole thing, we can't pair AI with AJ if there is another string with same suffix as AJ. This is AJ and has AI 0. A0 is this thing, the first letter of current string as starting letter. So since we couldn't map lime and coffee because there was another string which had same suffix and it had a starting letter which is same as AI0, which is loffy. So this is the whole whole case. What's happening here? We have three. So we have concluded with three conditions. So you can go through the examples and possible examples and see if there's any other case. But after spending some time, you can conclude that we have only these three cases in which. So this is also an invalid case. So we have three cases in which we can't map any string A with AJ. Okay. So all the remaining cases we can map A and AJ. Okay. So if we just remove these cases from the total number of cases, we can easily find the answer. Okay. So let's see how to remove these cases. Okay. So we saw that we couldn't map any string A with AJ which had the same suffix and starting letters, right? So let's just group all the letters together, all the strings which have same suffix together, right? Coffee, toffee. Okay. So they have. So we identify this group with the suffix, with their suffix, OFFEE. Okay. And one more string we had was time. It had a suffix IME, and another string we had was donuts. Its suffix was ONUDS. Okay. Now we have a different way of representing the given string, given set of strings, right? So now we, instead of having an array and then checking whether we can map or not AI with any other left elements, we can transform the array into this representation in which we store for each suffix, we store all the strings in the array present in the array which have the same suffix, right? So the reason why we do this is because we just saw before that even if two strings don't have the same suffix and same starting letter, there is an indirect connection in which we cannot map those two strings. So in that indirect connection is the remaining strings which have same suffix with the string which we are trying to map and have ended up having the same starting letter of current string, right? So in order to ensure that we don't count those strings, we have to we have to convert this given array into this representation where we have a suffix and we map for each suffix, we group all the strings in the array which have the same suffix. Okay. So now we will do the same thing, but instead of in a linear fashion, we'll if let's say we are at time, and we'll instead of going through the left, we'll be going through all the previous groups which are present before I'm, and we'll check if we can map time with each of the strings in that group. Okay. And you could have noticed one more thing, that what if the current group has had two more values, right? And we saw that we can't map two strings if they have the same suffix, right? So the current group represents a set of strings which have common suffix. So we cannot map any string with any other string in the same group, right? So we cannot map toffee with coffee because they are in the same group. So that's one thing to remember. And now we will do this thing. Yeah. Now we will go through each and every group, and we will try to map each and every string in the current group with all the strings which were present in the previous group, right? And again, we cannot do that directly. We have to have some sort of information, right? And that information can come from any data structure or any other way. Okay, let's see. Usually, how do we do? Let's say we are trying to solve the problem of we have an array, and we need to count for each letter. We need to return another array. For each letter, we need to return how many characters which were present before that letter, which is present before that value, which is equal to that value, current value, right? So in this case, it would be 1. In this case, it would be 0, 0, 0, 1, 0, 2, right? So in this case, it would be for 2, there was one value present before the current index, which was 2, and for this 2, there were two 2's before this. Okay. So how do we do this optimally in linear time with some data structure? So we'll use a hash map, and we'll store the frequency of all the values, and then when we come here, we'll just add count of AI, right? That's how we do to the answer. Similarly, we'll use the same logic here and store some information till the current index I, which will add up to our answer. So this is also an important thing, like that fixing an element technique. Just storing the information, storing the state of some data structure till the current index I, and using that information, using the data structure, and using the information from the data structure to update the current answer. Okay. So in this case, we saw that in order to be valid, in order for two strings to be valid, they shouldn't have same starting letters, okay, or same start, and then no same suffix, and then there was an indirect connection, right? So that indirect connection can be written as if we have, let's say we have a, let's say we are at a current string AI, and the first character AI of 0 is x, sorry, x is AI of 0, okay. Let's say we have x, and we are trying to map in any previous group, we are trying to map the current string, right? So the first thing is that in that map, in the previous group which we are trying to map, in the group of that string, there shouldn't be any other string which had the same current character, right? So in any previous group, no string should have aj of 0 equal to x. Okay. So if we just store those strings which doesn't have for every string in the group, if we somehow store what all starting values which are starting letters which are present in that group, we can easily say that, okay, now we are with this string, and I'm at this string. Can I map Hoffian time? Okay, I cannot map because there was a string which was present in the same group which started at t. So somehow if we have a data structure which stored this information that for every current character for every current character x, and for every current character x, there shouldn't be a there shouldn't be the same any string with the same character starting letter in the group we are looking at, right? We need some sort of information like this. So let's just call this let me just remove let's just call it as count of xy. So count of xy means for for every for x as a starting letter, in any previous group there shouldn't be how to put this. Okay, let's look at an example and then see. Let's say we are at time and we are trying to map each and every string everything in the previous group, right? And I told that we cannot do that directly. So how do we do that, like indirectly, right? Let me explain this count part later. So when we are at the string time, we want to find the contribution of this string time, right? So we try to map all the previous letters with the current all the previous string with the current string, and we see what are the possibilities, right? So in the worst case, what could be what are the different possible strings we can get? We can get AAME, we can get BAME, we can get DIME, and so on. We cannot get TIME, so we'll get SIME, and then we'll get UIME, and so on till ZIME, right? So these are the possible strings we can get after swapping the first letters with any other string in the previous group, right? So we cannot get T here, we cannot get TIME because it's the same string, current string. So we can see at most there would be 25 possibilities. Let's just say 26, and we remove the current possibility, which is 10. Okay. So what we do is we just similar to the fixing an element, fixing an element strategy we followed for reducing the time complexity from order of n square to order of n. Same we use here. We just fix the starting letter of all the possible strings which can form. For example, let's just say we want to find all those strings which were present in previous group, after with which swapping the current string we will end up getting AIME, right? So those strings will have A as a starting letter, okay? And so those strings will have A as starting letter, okay? Similarly for BAME, we will try to find all the previous strings which had B as a starting letter, and we'll only then we can get BAME, right, after swapping in the previous groups. Okay. So similarly we will fix all the possibilities. So there are 26 possibilities. For each possibility we'll check. So let's say we are at A and we want to convert time to AAME, right? We want to convert TAME to AAME. So we can only convert this if there was a string before in the previous groups which had A as the starting letter, and this is an important thing, and it doesn't have T anywhere in its group. So now I think it's clear why we need this data structure, right? So this data structure represents, let's say count of A comma T. So you could have seen here this count of A comma T represents total number of strings present in previous groups which start with A and doesn't have T as a starting letter for any of the strings in its group, right? Let's see an example. If when I say count of A comma T here, it means the total number of strings which were present till now, till this index, which started with A. Okay, in this case no string started with A and it doesn't have a T in its group. So that's what this count of A comma T represents. So if we have this information, we can directly add this to our answer, right? So this is what we want, because we just ruled out all the possibilities. So the first case, which was having two distinct values, it's already rolled out, since I said the list only contains unique values. And the second case that we need to check the whether the newly found string shouldn't be present. So essentially we just have two conditions, and the first condition is the unique condition we already saw. Only one more condition to rule out, which is this case, right? There was one more condition, that they shouldn't have the same suffix, but that was already taken care when we grouped the strings, right? When we group the strings, we will not try to map any of the string with the other string in the same group, right? Because the suffix should not be the same. So this is also taken care of automatically when we convert this array into this form of representation. And another case of unique characters is also unique strings are also taken care of in the question itself. So the only case in which the pairs become invalid is this case, this count of A comma T case, in which we need to find these strings, like we need to find these set of strings. Okay, let's just look at one more example and then look at the solution, right? So let's say we have an array with CIN, TAN, CAN, TAN, TAN, FAN, and LOL, TOL, right? And if we convert this into that representation, it will have CAN, TAN, AN, CAN, TAN, PAN, FAN, OL, LOL, TOL. So as I said, we cannot map any two strings in this group together. We cannot map any two strings in this group together, right? And the next thing we will say here is, let's say we are at CAN, right? We'll say we'll check out all the possibilities for X in A to Z. And yeah, and one more thing to say here, I forgot to say. We cannot in this X, it cannot be AI of 0, the current starting letter. Also, it cannot be any starting letters, any letter which is a starting letter in the current group also. Because if we let's say swap these two characters, we have another string tan, right, in the current group, but it's not possible. So X cannot be the current character. Also, X cannot be any character which is present in the current group also as a starting letter. So this is one more thing. Yeah, for X in K, we will have a check here. Check for validity. Only if this passes, this check will map, right? Yeah, we cannot map with CAN because they have same starting letters. So we will add to the answer count of X with what? With the C. So as I defined, count of X comma C here represents total number of strings which are present in the previous groups till now, which has X as a starting letter but doesn't have C as a starting letter in any of the strings present in the previous group. So in this case, one of the possible strings could be CAN. If you try to map CAN with CAN, it won't be possible because it has a C, because they had same letter. If you try to map TN with CAN, it's not possible because TN had another string which had C as a starting letter. So this would be a count of C with C would be 0 here. Yeah, I think this is clear. And the way in which we will check, we'll have this check of validity that X is not present in the current group of strings is by having another data structure in which we store some sort of information from which we can directly say, okay, whether X is present in the current group or not, in any group or not, right? So one more common technique we use here is the bitmasking technique. So what we will have is we will have two data structures. So one data structure to store this mapping of suffix with the set of whole strings, and another data structure to store the suffix with the bitmask, some sort of bitmask. And that bitmask, it will have a length of 26, and the bitmask represents the set of letters which are present as a starting letter in the current group, right? In this case, let's say in this case the bitmask would be let's say, so it will be in this reverse order, but I'm just writing it from left to right only. In this case it will be 0 0 1 and 1 0 0 something, right? Because A is not present, B is not present, okay, C is present, and then after some time T is present and nothing else is present. So we'll be storing that here. For each group we'll be storing that. So why we need this? So we need this in order to optimize this check. Like we can't just go directly again go through the entire group and check whether there is a string which has X as a starting letter, X or C, right? So if we have this information, we can directly look at this bitmask and ask, hey, do we have C as a starting letter in this group? So we can directly look at the bitmask and query the second bit and see if it's set or not. So if this bit is set, we can say that okay, current group has any group has the C in its C as a starting letter. It's somehow difficult to explain this mapping, but it will be clear after seeing the code. So yeah, we'll look at the bit and see if it's set. Okay, we cannot. So if it's set, this check will fail, and we'll move on to the next letter. So for A, the check won't fail because this bit is not set. So here we'll basically be checking whether this bit mask contains the x minus ath bit or not, right? Because x is a character. Okay, so we'll do that, and I said we'll be traversing to group by group, right? And in each group we'll be looking at each string, and we'll try to add the contribution somehow. And before doing that, we'll be also we'll have another for loop for 26 iterations, wherein we try out all possibilities, all possible starting letters, right? AIME, BIME, and so on. And during that, we'll have this count. We'll add the count, and before adding the count, we'll have a check whether the current starting letter is present in whether this x or any letter is present in the current mask or not, right? Okay. So yeah, let's just look at the code and then again see, and then let's discuss the time complexity later. Yeah. Yeah, as I said, we have two data structures. These two data structures. I am using an unordered map to store these mappings, like from suffix to a set of strings and suffix to a bit mask. And yeah, so the first map will be called masks, which will store for each suffix what is the bit, what is the mask. So that mask represents, I told, the set of starting letters which are present in the current group. So yeah, so the masks map will represent this data structure, and the next data structure is the next map is have a the next map has a string and a vector of string. So it will represent this data structure where we have a suffix and set of strings, the group. So I call it groups, and then so we need to find this in order to have this check. We need to have this information already stored, right? So we'll first form the groups, all the groups, and then we'll form all the bit masks. Only then we'll start with the solution. Okay, so the first step is the preprocessing step, in which we iterate over the strings, and then we say the suffix. As I told, it starts at the first index and ends at the last index. We take that suffix and we put it inside a group, and in that group, in the group of that suffix, we push back the current string AI. Okay, and to find the mask, which is the bit mask, so for each suffix, I told, for each suffix we are storing a bit mask. So for each group, so each suffix represents a group. So for each group, the masks of a suffix would be this line, this just represents I'm going to this group. I'm going to this group. Initially, every group will have 0, 0, 0, right, till 26 zeros will be there, and I'm going to that respective group, and I'm saying find this some let's say fourth bit. Find this fourth bit and set it and set that bit, right? So in bit manipulation, we can do it like this. If we just do a r with 2 power 4 with this value, right? I am just writing it in reverse order. If we do an 2 power 4, if we do an r with 2 power 4, this bit will become set. So that's how we are forming the bit mask step by step. So I will go to the bit mask, and I'll say set this bit. That bit will be AI0 minus A. So here this will be the starting letter minus A, because starting letter is a character, so we need an integer here. Yeah, I will set that bit. We can also just do plus here, like instead of setting we can also do plus, but R is a bit faster, bitwise. Okay, and then we have a answer, long ans, and then the data structure I told before, count, count of 26, 26. Yeah, we have a 26, 26, 26 cross 26 matrix because the total number of possible characters is at most 26 in both the cases, right? Because only then that's how we see both the inputs of both the dimension is a character, and at most we can have 26 character, 26 lowercase characters. That's why we have a 26 cross 26 matrix. Okay, and then as I said, we'll iterate over all the groups, and in each group we'll iterate over each string, and for each string, let's say time, right? Let's say time, we iterate over all of its all possibilities, right? So we are doing that using another for loop which runs from 0 to 26, and this for loop represents each character from A to Z, right? And I said we will have a check, this check, this check, that check checks whether the current starting letter is not, this I is not present as a starting letter in the current group. So we can we can first get the current mask from masks of suffix, and then we can check if the ith bit, basically the ith character, is present in the bit mask or not, in that current group or not. To check that, we just need to make a AND with 1 power I, sorry, 2 power I, and it will tell us whether the character is present in the group or not, current group or not. And then we'll add count of I comma a 0 minus a. So this here is saying that I want to add the count of all the strings which starts with I as a starting letter, and it doesn't have any string started with A0, the current starting letter of the current string AI, in its group, right? So this basically means if I have pan, it just means I will get all the groups before the current group. I will pick up all the strings which started with P, and it shouldn't those string, and for each of those string which we picked, we'll again select those strings which which doesn't have P as a starting letter in any of in its group, like in any other string, right? So in this case, we'll see a tan, and we'll let's say we want to map C. From tan, we are trying to map. We are trying to, from all the checking all the possibilities, we want to form can, and we are checking we are picking all the strings which started with C, and only those which doesn't have T in its group as a starting letter. So this won't be a possibility. So that's what. So count of I comma a of 0 minus a represents that thing. So it's kind of difficult to explain in a single way, but if you just do it for each example, it will be clear. Yeah, and then once we do this for each and every string in the current group, for the next iteration, like for going into the next group, we need to update the status of our current group, right? So we'll go through the current group, and then we'll update that. Okay, for each character, for each string in the current group. So we found a string which had this character as a starting letter, and it doesn't have I in its group. So what does this I represent? This I represent those letters which are not present in the current group. So you get the idea, right? So when we go to the next iteration, this current group becomes the previous group, and this I represents this thing. So I hope it's clear. And then once we update, this whole thing goes on for each and every group, and then in the end we need to return twice the answer, because this thing just checks for every AI, it just checks all those strings which were present in the before, right? So as I said before, if we can map A comma AJ, we can also map AJ comma AI. So hence we need to return the twice of answer. And and regarding the time and space complexity, I have made a LeetCode post. This solution can refer here if you want. So that I have made a complete time complexity analysis here, you can see here. So the pre-processing this step takes order of 9 times n time, because we are iterating over all the strings, and for each string we are processing the suffix, this step, this line of that string, which can have length of at most 9, right? Because the maximum length will is 10, and if we remove one character it will have remaining 9 character. And yeah, so for each string we are doing this. So time complexity, the runtime would be order of 9 times n for this particular step. And then in the actual algorithm, for iterating over all the groups, so there are at most, in the worst case, there could be order of n groups, because if all the strings have different unique suffix, it would be order of n, right? So, and in each group we are doing 3 things, right? So first we are getting the current mask and storing it in this variable. And for getting the current mask, as I said, we need to process this suffix, and processing a suffix takes order of the length of that string, which is 9 in this case. So yeah, that's the next thing. Next we are doing some other processing. We are updating the answer for each string in the current group. So for each string AI in the current group, we have a loop that runs 26 times, and inside that we have a bitwise operation, this bitwise check and operation, and bitwise left shift operation, and that's order of 26. So this is a constant time operation, right? Because it doesn't depend upon the input n. So whatever the number of strings could be, we will still have a loop that runs 26 times for each string. So it's independent of n. So, and one more thing here is that note that I'm considering the cost of the bitwise operation is order of 1 here, although some people, this is one more thing for this. You can refer this article, this discussion basically, wherein they have mentioned why it's order of 1 and it's not order of log of 26 or something, right? For that you can refer. So this whole part takes order of 26 time. Yeah. Then at the last we have a loop that runs 26 times for each string in the current group, and update the count matrix. That's order of 26 again. Yeah, this thing. Okay. So summing up, we have order of 9 times n plus n times. So this 9 times n coming from the pre-processing step, and the next thing comes from the actual algorithm which we are talking about, this thing, right? And as I said, for traversing all the groups, and in each group we are doing 3 things, and the 9 plus 26 plus 26, it would be order of 9 times n plus 61 n, and asymptotically this is equivalent to order of 61 n. Okay, we can still say this is asymptotically equal to order of n, but to be specific, this is order of 61 n if we are considering about the constant factor and something. So usually so this is kind of equivalent to doing twice. This time complexity is equivalent to twice of I'll say this order of 61 n is equivalent to order of 2 log n, 2n log n, because n is there, and log n usually in most of the cases would be 32 or something, like 16 or 20 or 32 something. So this is equivalent to 2 or 4n, let's say 4n log n. So so if we are like doing some sort of binary search or something, this time complexity would have been in terms of logarithm, but even though the runtime is still same. Okay. Yeah. And for space complexity we are using 2 hash maps, and each hash map can have up to n strings, and each string can have at most length of 10. So space complexity would be 10 times n, because for each string it can have at most 10 characters. The solution, you can see it's like it has a pretty good runtime. You can see the solution beats 98% of the A++ solutions. Like, although it doesn't have good memory consumption, it is a good runtime. And yeah, we have an AC solution. And yeah, that's it. So the reason I made this post and video is because there were only few solutions. Like if we go to the discuss section and search for Bitmask, yeah, right now it's there. But when I was making the solution, there are only, you can see, only few videos, few articles, and even they haven't used bitmasking that much. So I'm not sure why this is the case, but like the maybe as I said here, using bitmask to improve the runtime, like in these kinds of string related problems, it's not very popular, I think. So yeah, hence the solution. You can read this article too if you want. So yeah, that's it. So yeah, the overall time complexity is order of 6n, order of 61n, and space complexity will be around order of 10n, and the approaches we are using is bitmasking and grouping by suffixes. That's it. Thank you.